Hello everyone, my name is Dan the Tutor. This is a clip from one of my weekly group tutoring sessions at the University of Delaware for Physics 201. If you have any questions, please leave them in the comments below. Thank you and enjoy. So now the second to last topic we're going to be talking about today, moment of inertia. So moment of inertia is essentially describing how hard is it to rotate an object. So there's an equation for moment of inertia. There's actually many equations for moment of inertia. There is a table, and in general the equation is this. I, which is moment of inertia, is equal to blank mr squared, where blank is a constant. There's a bunch of different moment of inertia constants, coefficients that you can have there. It can be 1, it can be 1/2, it can be 2/5, it can be 1/3, it can be 1/12. It all depends on what object you're looking at. There is a table that describes it. I don't have the table on me, but I'm going to be helping us out for the problems today when it comes to finding moment of inertia. Okay, so this is good. Now, there's one more thing I want to say about moment of inertia, and that is if you want to find the total moment of inertia, in other words, if you have multiple objects and you want to find the total, the total moment of inertia is equal to I1 plus I2 plus ... however many objects you have. And we're going to be looking at an example today where you have two objects and we're going to be adding the individual moments of inertia together to get the total. And one more thing, just in general, if you have a higher moment of inertia, a higher I value, it means that it's harder to rotate. Moment of inertia is all about how hard is it to rotate the thing. Okay, anyone still writing? So let's get into this question here. Number 1, what is the moment of inertia for the dumbbell rotated about its center? So we see here we have a dumbbell, like 10 kilograms on each side, and we can assume that the bar is weightless, or else I would have included it. But the important thing is that the axis of rotation is in the center, and the whole thing is 1 meter long. So here's what I'm going to say for moment of inertia. I equals blank mr squared. Now for these objects, we are going to consider them as point sources of mass. And that's important, and here's why. You don't have to write this down, you can just kind of watch this and take it in. There's a few different shapes we can have for moment of inertia. One is we can have a hoop. The hoop is hollow everywhere except on the outside of the ring. I drew this dot in the center to recognize that that's the axis of rotation, it's the center. For a hoop, the equation is I equals mr squared. Again, you don't have to write this down, you can Google a table online, because no one except for me and maybe your professors actually know this, what most of the moments of inertia are. And you don't need to. You can actually, I would say, you pretty much have to use a table for most of these problems, or they have to tell you, because there's just so many to memorize and it's very annoying. Then you have the solid disk example. So the solid disk, imagine something like a tomato can or a bottle of water or something that's not hollow in the center. There's stuff inside of it. Disk. A frisbee would work as well. For this example, I is equal to 1/2 mr squared. Then there's a bunch of different shapes you can have here, but these are just two common ones. Now, notice for both of these, the axis of rotation is in the center. Everyone see that? The thing is rotating about its center. So I'm going to go back now to our problem. Notice this looks like it's in the shape of if it's a dumbbell, it could be like a cylinder shape, it could be a sphere. But the point is this, these dumbbells are not rotating about the center of the dumbbell. Oh no, they are rotating outside of the center of the dumbbell. Why is that important? Because that means they're point sources of mass. If it's a mass like this that's not touching the axis of rotation, it's a point source of mass. Why is that important? Because it means the moment of inertia is 1 mr squared. In other words, just mr squared. I'll erase the 1. But this is the equation for a point source of mass. Now again, if we want to find the total, we have to find I1 plus I2, the moment of inertia on the left plus the moment of inertia on the right. Luckily, this is symmetrical, so they will be equal. And we also know, well, I probably should have said this, it's exactly in the, I did say it's in the center. Great. So this distance is 1/2 meter. This distance is 1/2 or 0.5 meters. which means my individual moments of inertia, like I1, is going to be m, mass is 10, radius, which is the distance to the axis of rotation, so 1/2, and I'm not going to say m because that's just the units, so 1/2 squared, which is like 1/4, we're going to get 5/2 as our moment of inertia I1. Again, I2 is going to be the exact same thing because the mass is 10, distance is 1/2, you square it, you're going to get 5/2. I total is going to be 5/2 plus 5/2. We get a total moment of inertia of 5. And in case you're wondering what the units are, they are not pretty. It's going to be 5 kilogram meter per second. Wait, this isn't right. 5 kilogram meters squared. Yeah, these units are terrible. So I would say you don't have to memorize the units. Of course, maybe you do. But if you do, luckily there's a really easy way to remember it if you're good at units. And that is, remember, I is equal to something mr squared. Since this is just a coefficient, it could be 1/2, whatever. 1/2 doesn't have units. But mass has units of kilograms, radius has units of meters, and we're squaring it. That's how I always remember the units for moment of inertia. I just think of whatever mr squared. And the mr squared tells me what the units are. Again, I don't think you're going to have to know the units on the test, but if you do, it's not too bad to memorize. Okay, any questions on this one? We got 5 kilogram meters squared for the moment of inertia. Is that high? Well, let's compare it. Let's compare it to, what if we put the axis of rotation on the left side now? Let's compare these moment of inertia and see which one's bigger. In other words, which one's harder to rotate. You can even kind of think of it right now, you know? What do you think would be easier to rotate, when the axis of rotation is in the center like this, or when it's at one end? It's a good question. Let's answer it. So for this one, again, I total equals I1 plus I2. Since the axis of rotation is on top of my dumbbell, notice if I call this like I1 and the right side I2, I1, it's going to be a mass of 10 kilograms times a radius. That radius is 0 because it's touching the axis of rotation. Everyone see that? So R is 0 there. And you can square it. It's still going to be 0. In other words, I1 is just 0. Then we have I2. I2, again, the equation is mr squared. So 10 is the mass. The radius this time, it's not 1/2. It's the full 1 meter. So 1 squared, that's 10. We add these up together. We get I total is 10 kilogram meters squared. There's our answer. Notice when we put the thing hinged at the end point, it's double when it was hinged at the center. In other words, when things are hinged at the end, it's harder to move. And that's going to be pretty much true for just about any object in physics. Like, I can't think of an object that doesn't hold true. Don't forget to like and subscribe. If you want me to start doing free weekly group sessions at your university, please post in the comments below or email me at dan@danthetutor.com. Thanks, everyone. Bye-bye.